Okay, so yesterday we mostly talked about ETH, and here it is to remind you. And today we're going to start by talking about ETH and 2D CFT, including the effects of Virasoro. Our first goal is to write an ETH like ansatz for the OP coefficients of a 2D CFT. That is, like in some regime where things are sufficiently chaotic, we'd like to have a random ansatz, which says that the OP coefficients are given by a smooth function of the dimensions and spins times something. So this thing is smooth, and we're going to determine it by bootstrapping Cijk squared. And then this thing is random, and will play the role of the random matrix in ETH. So it's just random numbers that are with mean 0 and variance 1. As a warm-up problem, we're going to consider this. We're going to quickly go through the case where you ignore descendants, and then we're going to include so we're going to ignore Virasoro temporarily. I'll go through that quickly because that's similar to what we did yesterday. And then we're going to go back and include the full effects of Virasoro.
Tom, sorry, before you start,
yes.
there's something I didn't get yesterday. So, CHHL, this was one application CFT of the ATH, no? Two
Yes.
heavy operators and one
Yes.
light operator. Now, why not three light operators where the two are actually the primary is light, but you take a heavy, deep descendants, which is over there, which is a heavy operator, in fact?
So
Why focusing on primaries?
yeah. So why not take something heavy that's a heavy descendant?
Yeah.
And the answer is that so the way you're supposed to apply ETH is to first use the symmetries to the maximal extent. And then it's as random as possible, consistent with the symmetries in the chaotic regime. Okay, so that means that if you have a big symmetry algebra, like the conformal algebra, you have to first organize under the conformal symmetry, and then it's only the reduced matrix elements, or the primary OP coefficients, that are allowed to be random. Because clearly the OP coefficients of descendants can't be random, can't be independent random numbers. They're fixed by those of the primaries. Good. Okay. So if we ignore descendants, so I'm just going to rephrase the ordinary ETH as a bootstrap problem. So let's look at the two-point function of some light operator on a torus in 2D CFT. So the torus is labeled by modulus tau. And we can expand in this channel. Now, if we were doing a true conformal bootstrap, then this thing would be a conformal block, a Virasoro conformal block on the torus. But I said we're going to ignore descendants for this warm-up problem, which means that the sum here is over all states, including descendants. That's why I'm calling this OP coefficient, I'm labeling it all, to remind you that this is the OP coefficient. This is labeled not just by primaries, but by all states. And in that case, what plays the role of the torus conformal block is just an exponential function. Because what are we doing here? We're inserting the operator O, then we're evolving by an amount z with the state I, and then we're evolving by an amount tau minus z with the state j. So this block here is just e to the 2 pi I z hi plus 2 pi I tau minus z hj times the same thing with bars on everything. So this is an exact equation, but since our goal is to bootstrap these OP coefficients squared in the chaotic high energy regime, the next step is going to be to basically what we do in the Tauberian analysis, which is to take an OPE limit. In this case, it's taking the imaginary part of tau to 0. So this is a high temperature limit. In the high temperature limit, the torus becomes a cylinder. And now you can do the conformal map, Z is log W, and find that this, and write down an answer for this torus 2-point function is just going to be the cylinder 2-point function, which is a well-known formula, which I'll write here just to remind you, e to the I pi h bar minus h, 2 tau sine z over 2 tau to the minus 2h times the same thing with bars. Okay, so that's the 2-point function on the cylinder that you get by the exponential mapping. And so now what we're supposed to do is just, we have this bootstrap equation. On one side is this pseudo conformal block expansion. On the other side is the cylinder 2-point function. And our goal is to solve for the asymptotics of these OPE coefficients. So we just have to invert this equation to solve for c squared. Now, since we're using the scaling blocks instead of the conformal blocks, this is just a Fourier expansion. Right? This is just a Fourier expansion in z and z bar. So it's very easy to invert this equation and solve for c squared. Just do the inverse Fourier to extract those coefficients. So you invert this by a Fourier transform, and that'll give you, that'll solve for C O I J all mod squared. I'll come back to this e to the s in a second, and it tells you that this is given by the cylinder 2-point function in momentum space. It's a function of omega and omega bar, where omega is hi minus hj, and omega bar is hi bar minus hj bar. So that's the whole calculation. I pulled just one little trick at the last second, which was in doing this inversion, I pretended that this is a smooth function. Okay, so I took this sum over discrete states, and I pretended that I was inverting it as if C was just a smooth function of energies. Okay, so that's where this e to the s comes from. I've converted the sum, I've approximated the sum by an integral with this e to the s, and it means that we don't actually get to extract the individual coefficients this way. What we're really extracting is the average over nearby states of those OPE coefficients because we've approximated the sum by an integral. Yes?
Sorry, I missed. The sum over INJ is the sum over primaries or over...
All states.
But if it's all states, then as you said, COIJ 27 is related to the primaries. So
That's right.
can you be sure that the smoothness is obeyed?
No, I don't think you can. So, well, I think you can. I haven't yet really assumed that. You know, at this point, I've extracted the average. So I think this equation is right. I think what you're telling me is that, well, I'm coming to the point that you're making. I think. Yeah. Was there another question here?
Are the two omegas the same? Is omega there? Z
No, sorry, that was the coordinate on the cylinder. No, different omega.
H plus H bar dependent?
Sorry?
Is there H plus H bar dependent somewhere?
Yeah, it's hiding in the, so this cylinder has a beta in it, and so it's hiding in there. It has a radius. Now,
Can I ask you another question?
yeah.
What is the error of this approximation?
What is the error? I don't really want to get into the error. I'm just going to talk about the leading terms. There are some things known about these errors, but they're pretty subtle. You have to be very careful about how big the averaging window has to be and details like that, which I don't really want to get into. The error depends on how big the averaging window is. Okay, so if we didn't know about Virasoro, and if there wasn't a Virasoro, we would just recover ETH in this form from this formula. So the name of the game is you use these Tauberian methods to extract the average of C squared, and then what ETH does is it's the guess that the individual matrix elements are just given by taking the square root of this equation and multiplying by a random number. So that's how ETH works. It's you take Tauberian to get the average, and then you just guess that if it's chaotic, that it's the obvious thing times a random number. Now we can't do that here because of Virasoro. This is what Tully was getting at. So we can't do that here. It's certainly not true that these coefficients are independent random numbers because this includes descendants and they can't be, so those OP coefficients can't be independent of each other. So to fix this and get the true thing that we're after today, we need to redo this calculation using, instead of using scaling blocks and Fourier transforms, we're just going to redo the calculation using Virasoro blocks and crossing inversion. Okay. And so we're really just repeating this ETH-like logic, but using the technology of the Virasoro algebra. So that's what I'm going to do now, unless there are any questions. Yeah.
I did not understand the opinion composition. Sorry, why there are two operators, why there's two indices to sum psi and j? Like you're not just using all with all, giving one operator?
No, this is the decomposition where you, so if there's an I and a j, so we're summing over both of them. So this is a decomposition where you do the thermal trace. It's like O, I, J, J, O, I, with E to the stuff.
Okay.
So it's that channel. Okay, so now we're going to do this using Virasoro. I'm going to go through this step by step and explain how to invert Virasoro, how to invert Virasoro blocks. So as a starting point, I want to define this universal function C0, which plays sort of a starring role here, and it's defined as follows. Take a Virasoro block for the identity operator. The external numbers here are label operators, so this is O1, O1, O2, O2 for two different operators. And write it in the dual channel. Okay, so in the dual channel, this is integral dh, rho 0 of h, C0 of h1, h2, h times the block in the dual channel. Okay, so what are all the things appearing here? This on the left is the Virasoro block, 1, 1, 2, 2 of the identity operator, and we'll call this channel 1 minus z. And on the right hand side, rho 0 here is the Cardi density of states, which is rho 0 of h. Well, there's an exact formula for this, but I'll just use the asymptotic formula. It's the exponential 2 pi root c over 6 h minus c over 24. this Hardy density of states is derived by inverting the identity character in the torus partition function. That calculation is reviewed in many places, so I'm not going to go through it, but you can ask me about it after. The last thing here is the Virasoro block 1, 2, 2, 1 at weight h as a function of z. And you should think of this equation as defining for you the inversion kernel C0. So for the Virasoro algebra, the complete inversion kernel was found by Ponsat and Teschner. Using technology from Liouville. The Ponsat-Teschner formula is general. It allows this weight to be anything, but the identity block is going to play the key role for us for the same reason that as what we just saw in our warm-up problem, that it was the cylinder 2-point function that was the input to that bootstrap, and similarly here it's the identity block that's going to be the input to this inversion. So what Ponsat and Teschner, they didn't write it for the identity, but using their formula, you can derive a nice formula for this C0, which is C0 of H1, H2, H3 is equal to the Liouville structure constant, that is the DOZZ formula as a function of H1, H2, H3 over the square root of rho 0 H1, rho 0 H2, rho 0 H3. There's an extra factor here, which I'm not going to write, but it's a known factor, and it's order c to the 0. We're eventually going to be taking the large c limit, so I won't care about that factor. It's sort of annoying to keep track of. Okay, so let me explain what's appearing here. So the Liouville CFT is an exactly solved theory in 2 dimensions that has only scalars. So it has a continuum of scalars, and so the 3-point functions in the Liouville CFT are just functions of three continuous weights, and it's a known function that was guessed and checked by Bootstrap by D and O and Z and Z. So the numerator here is some sort of complicated but known function. So this is just a totally explicit formula, which I'm not going to write down, but is written in closed form. And on the bottom, we just have some density of states factors. In Liouville, you mean?
Oh, C0?
So this formula is true as written, but so far, okay, so you mean C0. So far C0, this is just a math fact about inverting the Virasoro block. Now we've inverted a chiral Virasoro block, so this is not yet a physics statement about CFTs exactly. For that we need both chiral and anti-chiral.
It's much more trivial. You have the square root factor in the denominator.
Yes.
So I'm asking if whether C0 should be squared in your integral or whether it's the first power.
No, it's to the first power. This formula is correct.
So just to be clear, so you gave this asymptotic form for root 0, but there is an exact formula for everything that is written on the board.
Yes. Yeah, there's an exact formula for everything. Yeah.
So we know that Taubera theorem is only true in the average sense. How do we know that C0?
Well, I haven't said yet what the implication of this is for CFTs. This is just a math fact about the Virasoro blocks. Similarly, like if you take an identity block, you can write an exact equation for the dual channel. Now, what that tells you about CFTs is another question, because then you have to think about when it applies. And I'm coming to that, but for now, this is just a math equation. Yeah.
So what's the integration range of H?
I'm coming to that too.
Sorry, C0 is the square of the three-point function then. Answering to Pat's question.
So, there's no 3-point function here yet.
Well,
I called it
C0
C, but it's just the inversion kernel for the Virasoro
I
block.
think it's the theme circle.
What?
The theme circle.
What about it?
Well, wondering whether it's square.
No, it's not square. So this is the Virasoro block. This is the chiral block. It's a function only of z. It's a holomorphic function of z. And there's just an integral over h here. It's not over delta, or h and h bar. This is a chiral equation. Everything's holomorphic in z.
In Liouville, this DOZZ, what is that?
Ah, yes. In Liouville,
Yes.
these are the weights of a scalar.
Yes.
But this is the 3-point function.
This is the two.
This is the 3-point function in Liouville. But this is not the 3-point function of anything. Yeah.
It should be squared then. See, there's a different function should be squared because there are two.
No, it should not be squared. I'm coming to, I will write it,
It's not squared. It hasn't called on the block composition of Liouville.
it's not squared.
Wait, so Liouville doesn't have an identity operator, right?
Sorry?
Should I be worried about the fact that there is no identity block in
In Liouville? No, because this isn't a statement about Liouville CFT. In fact, I haven't yet made any statements about CFT. So far, I just made a statement about Virasoro conformal blocks.
So this first equation is purely kinematic.
Yes. Yes. It's just a statement about this chiral block. Exactly. Good. Okay, these are good questions. This is important. Does this make sense? So this is just a math statement, and I'm going to get to the physics statement that you can extract from it in a minute. Yeah.
I'll add a comment, which is that normally if you write an S-channel, try to write an S-channel block as a sum or integral over T-channel block, which is exactly what you're doing here. For ordinary conformal blocks, we know this cannot really be done because you have derivatives of blocks. If you expand the block around the wrong end, you see that it doesn't have a good expansion in T-channel blocks. So the magic of this kernel, this Ponzo attachment, is quite a nice result in itself about Virasoro blocks.
Yeah.
I'm not sure for which values of C and H it exactly works. You're already going a little bit beyond what they did, and I only know their paper. But there's this magic that you can express an S-channel Virasoro block as some infinite integral over T-channel Virasoro.
Yeah.
And it's quite a magical formula.
Yeah.
I think it's nice.
Yeah.
And yeah, I don't remember factors of 2.
There's something very weird about it, right?
That's what it is.
In higher dimensions, you can write the blocks, but there's no kernel. In 2 dimensions, you can't write the blocks, but there's an exact formula for the kernel.
It's a messy formula.
It's a messy,
We're having
yes.
a lot of mess, but
But
it's an explicit formula, which is really nice.
Yeah, if you put a general weight here, the formula's really awful. Like it took me like 3 days just to understand what the formula was saying. But the formula with an identity here, which was derived by Scott and collaborators, that formula is just this, which is much simpler. You can just evaluate it. So the
Sorry,
yeah.
what's the integral control of H? It's a
Sorry?
real number or?
Sorry,
What is the integral contour of H?
I'm coming to that right now.
Oh, okay.
Contour. Okay, so the contour here, integral dh, really means there's two parts of this. There's a multi-twist discretum, and then there's an integral dh from c minus 1 over 24 to infinity. Okay, so the way to think about this is that you start by writing this formula where all the weights are heavy, meaning above c minus 1 over 24. You start by writing down the formula where all the weights are heavy, and then there's an exact formula. And then you have to analytic, and now to get the answer when some weights are light, you have to do an analytic continuation in the weights. Sorry, when they're all heavy, you have only the continuous part. Now you want to take some of them to be light. Some poles will move off into the complex plane, and you have to keep those poles. So that will give you these discrete states. So it's understood how to do that. It won't really be important for what I want to say, so I'm not really going to get into it. I will. But let me say a bit more about it in the semi-classical limit. So the semi-classical limit means you take c to infinity with h over c held fixed. So in the semi-classical limit, I'm going to parameterize the weights as c over 6 times eta 1 minus eta. This is a parameterization that's useful in Liouville, but also in 3D gravity. So that's just a definition. If h is less than c over 24, then that means eta is a real number between 0 and a half. And in that case, I'll call these operators conical defects, because that's what they're dual to in ADS3. If h is greater than c over 24, then eta is equal to a half plus an imaginary number. And in that case, I'll call these operators black holes, because that's what they're dual to. And this statement about the multi-twist discretum is the story of Virasoro mean field theory, so Virasoro MFT, and what it says in the semi-class, what you find by this contour argument I was describing in the semi-classical limit is that if you have two operators whose etas add up to less than a half, then you get an operator, then you get a double twist operator O1, O2 with just the sum of the two etas. Otherwise, there are no multi-traces, you just get the continuum. So unlike ordinary mean field theory, so in ordinary mean field theory, if you take two operators, then you get this whole family of double twist operators labeled by N and L. In Virasoro mean field theory, things are a little bit different. If the operators are light enough that they're below the black hole threshold, then you do get composites, but instead of the conformal weight, the conformal weights don't add. Instead of the conformal weights adding, it's the etas that add. So that's why it's nice to write it this way. The etas are related to the defect angle in ADS3, and the fact that the weights don't add is the fact that there's some binding energy of conical defects even when they're very far apart. So if they're light enough, you get these composites, but then the spectrum of the discrete spectrum of composites gets truncated at the black hole threshold, and above that you have a continuum. So that's how mean field theory works with Virasoro.
Question. Is this Virasoro mean field theory most actually formulated in this polymorphic way, or should you always try to pair it with anti-holomorphic weights?
Well, I think of it this way, but I don't know if yeah, I'm only going to think about this chiral way. Maybe Scott wants to say something about the non-chiral case.
It governs the large spin, but it universally goes to large spin dynamics in CFT, so it's effectively chiral. If you take one weight to infinity and the other weight is fixed, and this controls the spectrum of twists where there are accumulation points in the spectrum. So it's effectively chiral, but really it should be thought of. It's only relevant for CFT in the chiral sense, but you do need to think about the whole chiral sense. Blind on that.
Okay, yeah, thanks.
Okay, so let's proceed. Remember, what we're trying to do is we're trying to use the bootstrap to determine the asymptotics of mod c squared. And now that we know how to invert Virasoro blocks, we can write down that formula. So let's think about the 4-point function O1 of 0, O2 of ZZ bar, O3 of 1, O4 of infinity. And we're going to look at this in a regime where it's given by the identity block, by the Virasoro identity block, mod squared. Sorry, I should have done O2, O2. This should have been 1, 2, 2, 1, so that we can get an identity block in the teaching. Okay, so when is this true? So this is true if in any CFT, if you take z near 1, then this will be given by the identity block. It's also true if we take c to infinity, we assume a large gap in the spectrum so that this is a holographic CFT, and we take z and z bar, and then for any z and z bar. Okay, so there are two situations where you get dominated by the identity block. One is in the OPE limit, and the other is in holographic CFTs. So the OPE limit is sort of much bigger in holographic CFTs. In fact, in this case, it's everywhere is the OPE limit, because it's the only operator. Identity is the only operator that can run there. Okay, so now we're talking actual physics. This is an actual CFT correlation function. We're going to apply what we just learned about the Virasoro crossing kernel to this equation. So we want to write down the conformal block expansion on the left and do the inversion. Let's start by let's do it in reverse. We're just going to take this right-hand side, apply the Ponsat-Teschner, or the universal C0 formula, and rewrite it as integral dh, integral dh bar, rho 0 of h, rho 0 of h bar, C0 of h1, h2, h bar, h. Same thing with bars. Times the Virasoro block in the dual channel. So what I've done here is I've taken these two Virasoro blocks, holomorphic and anti-holomorphic, and applied the inversion individually to both of them. So now we have it written in the S channel, and now that it's written in the S channel, we can just read off the asymptotics of the OPE coefficients in the S channel. And we learned that C1 to I mod squared averaged over nearby states is approximated by C0 of H1, H2, Hi times the thing with bars. So that's the physics formula. And that's what we were after. This derivation, as I described it, so we should ask when it applies. So this derivation was for the light heavy case. That is, we were thinking of O1 and O2 as light operators, and then looking at the heavy operators running in the O1, O2, OPE. So where it applies, from this derivation, what we derived was that this applies as you take HI to infinity, with H1 and H2 fixed. They actually don't have to be light, they could be anything, but they're much lighter than HI because you're taking that one to infinity. Yeah.
Just clarify, is this for holographic CFTs or more generally?
No, I'm about to write that. Okay, so this is i.e. We've derived this for HI to infinity, or for holographic CFTs and HI bigger than C over 24 or C over 12. Actually, exactly where that cutoff for exactly where it applies in holographic theories, I'm not aware of anyone carefully working that out. But it's, well, presumably it applies above the black hole threshold. The natural guess is it applies above the black hole threshold. That's something that we should be able to derive by using the gap condition and looking at this inversion carefully, but I don't know if that's been worked out. Yeah.
And what point did you take at H large? Where is the stuff around?
You mean in the holographic case? So, yeah, and so if we're not in the holographic case, then when I said that we want to work in a regime where this is given, so non-holographic, if you're non-holographic, in order for this to be the identity block, you have to take z to 1.
Yeah.
And then that means that the dominant contributions to this inversion integral are happening at large h. So you're learning about the asymptotics at large h. In the holographic case, if there's a large gap, then the only states appearing in this OPE are the heavy states above the black hole threshold. So you just learn about the OPE above the black hole threshold. So this derivation was for light, light, heavy, but exactly the same formula.
Sorry, Tom, you just said now that holographically in the OPE of O1 and O2 you only have heavy states?
Well,
why would that be?
there can be light states, but there are very few of them. And so if we take as long as we take z not too close to as long as we take z not too close to 0, the dominant contribution here is still going to look like an identity block in the dual channel. There could be some small prefactors coming from the fact that you're exchanging some states, but it won't affect the exponential dependence of this thing, which is all that we really care about in the holographic case. There are corrections to it from other light operators appearing in the
Just to be clear, so rho naught was just a mathematical object in this inversion, but it happens so that it coincides with the Faraday density of states at leading order, and that's why identification becomes so easy. Some leading corrections.
Actually, well, rho 0 was just put in by hand for convenience in the definition of, when we defined C0, we stuck in a rho 0 by hand, just in order for this formula to be true without any extra e to the s's. That was just put in by hand in order to get a nice, it's part of the definition of C0.
But so rho 0 is independent of the t, depends only on the central charge.
Rho 0?
Rho 0 beside the leading order also depends
Right.
only on the central charge. That's the statement.
Yeah, that's right, yeah. Yeah. Okay. So exactly the same formula for that OP coefficient holds in the for the cases light, heavy, heavy prime, and heavy, heavy prime, heavy prime prime. So in other words, this formula is true not only in the case where I just derived it, but if you take any of them to be heavy.
Sorry, I think you answered this stupid, but just to confirm my understanding. So if you don't have like strict large gaps, if you have a few light operators,
Yeah.
you say their blocks are just proportional to the block of the identity, and then just a prefactor that changes in the holographic CFT?
Let me think about that for a second. Yeah, basically because this, so in the bulk dual, this is some conical defect geometry that looks like this identity block, and that has large back reaction. So the gravitational action is the dominant thing here. Now you could put another light field in here, but it's just going to address the gravitational action by a small factor.
So you mean there's an exponential part that goes with C,
Yeah,
and then there's a prefactor that depends on how many light fields you have,
that's right.
and that prefactor will also appear at the end.
That's right. Yeah.
Tom, sorry, in the non-holographic interpretation, H, how do you characterize when a frequent operator is heavy?
It's an asymptotic formula, and
Because there are
don't
there
really
is an
know.
H which is related to the OP, which is the exchanged one, but now you have also the external. They might even be parametrically
Yeah,
different, so to say. no?
yeah.
So how do you-
Well, you're talking about in this one. It's clear that what you're supposed to do is take the heavy one to infinity with the other ones fixed.
Yes.
In this one, at least the one I know how to derive, you take them to infinity at the same rate with the other one held fixed. And same goes for this one. Now, I suspect you can also take them in various ratios, but I haven't thought about it.
A comment that might be worth making about the contribution of other light operators in the T-channel is if you consider the contribution of some other light operator but above the identity in the T-channel and invert it, then the inversion kernel will be exponentially suppressed compared to C0 in the limit where you take the weight large, or in the semi-classical limit where you scale it with C and then take C to infinity. That's just a consistency check of everything you're saying.
How can it be, I think it's going to affect the prefactor. How can it be exponentially suppressed?
Shouldn't it just be another Virasoro block that you write down?
Yeah, I think it'll be equal up to it'll be equal to the identity contribution up to small corrections.
Well, at least in this non-holographic setting, I think it is exponentially.
Oh, really?
suppressed
Okay.
compared to the-
Okay.
Yeah.
Okay, that makes sense in the non-holographic
Yeah,
case.
yeah.
Okay, so let me see. I'm going to skip something. Well, let me just make a connection to our warm-up problem quickly, which is the case of light, heavy, heavy prime. Okay, so I won't go through the details because I want to keep moving here, but how would we derive this formula for the case of light, heavy, heavy prime? In that case, we would look at the two-point function on the torus, and we would expand in these Virasoro blocks on the torus, and then this looks very much like our warm-up problem. Okay, so in our warm-up problem, we expanded in just states going around the torus. If you want to derive this formula in the light heavy prime, you should expand. Now this is some of our primaries, and this is a true Virasoro block. And then you want to invert this. We want to set this equal. So the way it works is you set this equal to 0, 1 at modulus minus 1 over tau. This is some other Virasoro block, and you want to invert this crossing relationship. Okay, so this is now a crossing equation, which you can invert using the Ponsonby-Teschner formula, and you'll end up landing on exactly that same formula for the OP coefficients C0 ij squared. So I'm going to skip that, but at some point I'll post my notes on the webpage, and if you want to see, it's only a few lines of manipulating some conformal block pictures, but I'm not going to go through it.
This loop that you drew with the identity and the minus 1 over 10, should I think of this as like, if it was tau, it would be like heavy operators so I'd round loop? And this is just handle, or did you mean?
Yeah, that's right. That's right. If you invert this, it becomes heavy. So this is the thing that will be the cylinder. This is like the cylinder limit of the two-point function if you're in a non-holographic theory. So this will be that sine. This will be the cinch formula.
The idea is that this very heavy operators are like create this state instead of the temperature.
That's right. Yes. Yeah. If you do the modular inversion on this, then you get a heavy state here, and that's creating the temperature in which these guys live. Okay. So now we're done with this calculation, and I can write up the conclusion. So there can be Virasoro ETH. It goes beyond ETH, but the ETH-like ansatz, I'll call Virasoro ETH, is, I'll write it for I not equal to j, not equal to k, so that we can drop the diagonal type terms, is that the OP coefficient Cijk is equal to the square root of C0 Hi Hj Hk, C0 Hi bar Hj bar Hk bar times a random number Rijk. So let me recap what these ingredients are. C0 is the Liouville structure constant, up to some Cardy factors. It's important that the left-hand side has discrete labels, whereas these C0s are just functions. They're just smooth functions of the weights. Okay, so this is a completely well-defined, explicit, known function of the weights, and Rijk is a random number with mean 0 and variance 1. So if we compare this to ETH in quantum mechanics that we talked about yesterday, then what you see is that this square root of the thermal two-point function is just being replaced by C0. That's just the difference between inverting the scaling blocks and inverting the Virasoro blocks.
Is it fair to say that for this formula to be true, at least one operator has to be heavy?
Yes. Yeah, I'm coming to when it applies in a second, but yes. So these random numbers are treated well. The ansatz that corresponds to ETH, so the strict leading ETH type ansatz is that we treat these as Gaussian random variables. So the average here is just the contraction delta IL delta Jm, delta Kn, plus dot dot dot, where the dots are permutations of that, and there could be subleading terms that are not strictly random. And since it's treated as Gaussian, that means that if we have something like R, if we have something like 4 R's, and we take the average of those, then that's given by Wick contractions plus corrections. So plus permutations plus potentially e to the minus s corrections to that.
Is it a result of discussion or is it an assumption?
This is, so let's see. So this is just an ansatz. The fact that the statement that is Gaussian is just an ansatz that is motivated by ETH. And as usual in ETH, you sort of have, there's sort of two things you can do. You can try to check it numerically, or you can just take it as an ansatz and see where it leads you and see if it's consistent with other things that you know. And that's what we're going to do, is we're going to compare to holography. Yeah.
Is it true that your ansatz applies to non-chaotic theory? Like if I took a symmetric product of a bunch of compact theories, you'll get the right answer and the right limit.
No, it's not. So this formula is true.
Yeah.
So this formula is going to be true in any theory in the appropriate limit, including in non-chaotic theories, integrable theories. But this formula is not. Okay. So when do we expect this to be true? It's the same as with ETH. We expect this to be true in the chaotic regime. Now we don't know exactly what chaotic regime means, but it should be true when things are as random as possible, and it won't be true if things are fixed by integrability.
Is a free boson at irrational radius, which is strictly speaking a rational theory, chaotic enough?
No.
No. No, fuck.
Yeah, if you can write that, if you can write it down, then it doesn't satisfy ET, most likely.
What about large M minimal models? They're kind of
also no.
Also no.
Yes. I think maybe they're well.
I don't think so. Large and models will approach a free boson.
Yeah, probably not. Okay. Yeah. Yes.
Do you make a theory to be holographic? Because generally I've seen chaotic theories defined as the ones that have like black hole begins.
Yeah.
Would you generally need the theory to be holographic?
I don't think so.
Okay.
I don't think so. At least for this ansatz, ETH just applies to quantum mechanics. So at least for this much, I don't think we need holography. I think that we should be able to apply this to the kinds of CFTs that we study numerically, but they do have to be chaotic, so like the rational models won't work. So the chaotic regime means one of two things. It either means that you're in a non-integrable theory and you're taking one of the weights very heavy, or it means that you're in a holographic theory and one of these is a black hole. At least one of them is a black hole. Okay, so in a holographic theory, you just need at least one of them to be a black hole, and then you're good, because black holes should be chaotic, but otherwise you have to take something asymptotically heavy.
Is it fair to say that holographic theories are like even more chaotic because the regime of validity of this thing is extended?
Yes, absolutely. Yeah. Yeah.
Are there any numerical checks?
That have been done? No.
But which theory should
Yeah,
apply?
exactly.
How would you do? You like Hamiltonian truncate? Or what? would be
I heard a rumor that somebody has confirmed ETH by Hamiltonian truncation, but I don't know the details of that. Most of the numerical checks in ETH are just in quantum mechanics. There's very little, there's no numerical check that's published in quantum field theory. Okay. So this is the ansatz that we're led to in theories with Virasoro. Now, so far, we've been discussing a fixed CFT. That is, this is a statement that's supposed to be true about a particular CFT that satisfies all the axioms of conformal field theory. And so in that fixed CFT, there's some particular values of Rijk, these random numbers. It's one particular draw from the Gaussian ensemble, or it acts like a particular draw from the Gaussian ensemble. But now, we're going to change gears a little bit and average over these random numbers Rijk. So why would we want to do something like that? Well, there are some cases in ordinary ETH where observables are self-averaging. Okay, we saw examples of that, like when we calculated the two-point function O squared. We did the calculation by averaging over these random matrices, but that's also the largest term in a fixed theory. So that's one reason, because there are some observables that are self-averaging. The other motivation for this is holography. And in particular, there's been a lot of work over the last few years in studying disordered theories with some randomness, like SYK, and the relation to higher topologies in ADS CFT. And so really, just because we can. The motivation of this is just because we can, and we're going to find that it has an interesting interpretation on the gravity side. Okay, so we're going to average over the Rijk, and starting now, we're going to assume a holographic CFT. For most of what I'm going to say now, we're going to assume that it's holographic. Now, this isn't, I don't think this is really necessary. There's no reason, we're free to average over these in a non-holographic CFT if we take this asymptotic limit. I just don't know a good interpretation for what that average means in a non-holographic CFT. In the holographic case, I'm going to give you an interpretation. Taking this average over these random numbers, Rijk, in a holographic CFT is a large C ensemble, not of CFTs, but of CFT data. Okay, because if I take a particular draw from this, so if I take a particular draw, I choose some random Rijks, then this is not going to satisfy crossing. There are lots of constraints that have to go in for this to be a true conformal field theory. It has to satisfy crossing exactly. And if I just pick some random numbers, it's not going to be satisfied. Okay, so this is not a true CFT everywhere in the ensemble. It's just a ansatz for the OB coefficients. We're going to average over it. Now, it will be crossing symmetric on average. And it'll satisfy the bootstrap on average. And that's why it still seems like a reasonable thing to do. But it's not that we're literally taking an average over well-defined CFTs. But I'm going to stop here for today, and we'll pick that up tomorrow.
sorry, Don, really, this is a trivial question, but the original ETH was essentially LHH, but we said that O has to be a sufficiently simple operator, let's say it's a light operator, and M&M should be heavy. Now in this Vitasor ETH, somehow we have extended the ETH hypothesis to a more general setup. Can you comment on that?
Yeah, I don't, yeah. Well, we don't know if it's true in general. So again, it's just sort of because we can. It's anytime you have a Tauberian theorem that tells you the asymptotics of something squared, it seems natural to guess that it's as random as that at high energies, it's going to be basically random subject to that Tauberian constraint. And so that's what we're assuming here. I would say it's in the spirit of ETH, but I agree it's not obvious, like if all three are heavy, that really fits into the idea of it being a simple operator. I think that if you take, yeah, so it's really just a ansatz to propose and then see where it leads. In the holographic case, it's going to be important that we do assume it everywhere. But if it's non-holographic, then I don't know.
But this suggests, so for example, in ETH, if instead of taking both states to be heavy, you just take one state to be heavy, is there still some validity, or it's known that it breaks down?
Like in quantum mechanics?
Yeah.
That's a good question. I don't know whether that's, I don't know what the answer is in quantum mechanics for light prime heavy. If there's a random, I don't know.
Can you speculate a bit more on how would we numerically test this ETH? What would be the simplest scenario, the simplest test?
Well, I think that, well, first of all, the fact that we're doing Virasoro is mainly because we want to use holography and it's easier to do holography in 3D gravity. I think if you wanted to test this numerically, you need a chaotic CFT that you can bootstrap. Okay, so like the 3D Ising model sounds like a good place to start. That's a chaotic CFT that we know how to bootstrap. So I think one thing we could try, for example, is to figure out exactly what ETH suggests for the 3D Ising model, and then try to push up the numerics to larger and larger twists until we can access that regime. I don't know whether it's feasible to be able to push the numerics that high, because I think it really has to be in the regime where you start to see random matrix-like behavior. It has to be in a regime where you have lots of states. But I don't know, what can we get now? A few hundred operators? So maybe if we could get a few thousand operators or something and really get up and twist, maybe you could see it. I don't know. Yeah.
Could we make a small comment? If we're talking about high-dimensional cities, then besides the off-diagonal gauge, there is a simpler statement, there was a diagonal gauge. So you would try to check that first.
Can you speak up a little bit? It's difficult to hear.
If we are speaking about high-dimensional cities, then besides off-diagonal gauge, there is a simpler statement of diagonal gauge. This is a statement that heavy light with the equivalent heavy is a smooth function of the dimension of the heavy. So that would be the first thing to check for the Ising model, but I still think that's beyond reach. So how you would do that? You would simply calculate heavy light with the equivalent heavy, put those dimensions, they should form a continuous trajectory with the oscillations becoming smaller as dimension of the heavy increases. I don't think that has been done, but that would be the first thing to check.
Yeah.
A question about where exactly does this? I understand that CTH is stronger than Tauberian theorems in the solar syntactics, but where exactly does it start to become different? Like, imagine if I take the average over states over a big window that is bigger than point one, then everything you said we know from Tauberian theorem.
Well,
it's about taking the window small, or what exactly is the?
I mean, the Tauberian theorems only give you a statement about this average, and yes, you can, if you take the window large, it's true in integral theories, whatever.
Yeah.
But this statement here is a statement about one particular state.
Yeah, okay.
So so it's like taking the averaging window to 0.
But then you do statistics over many nearby guys, because you can't,
Well,
decide whether something is drawn from the distribution by looking at one graph.
Well, let me tell you what would happen like in the 2D Ising model, okay? Because I know what happens there. So in the 2D Ising model, well, we have to talk about scaling as opposed to primaries because you don't have asymptotic primaries. But if we talk about the scaling, just the states in the 2D Ising model, then they live in the different primary families. So there are only 2 primaries, and what you find is that this formula is true. But the individual ones sort of go like, they jump around like this because of the 2 families. So the individual ones do not satisfy, are not given by the square root of this. The one family is systematically larger than this formula, and the other family is systematically smaller. And they jump around not in a random way, but in a pattern, up, down, up, down, up, down. So no formula like this is going to be true in the 2D Ising model.
Yeah.
Does that answer your question?
Yeah, so it's really about caring about individual parameters.
Yes.
Did you need to write an R in front of that square root, or?
I think you used it also.
Yeah.
Oh, did I?
Because the
What happened?
yeah.
Yeah.
In which case it's the same as Ising, instead of just jumping up and down in a regular way, jumping up and down some chaotic way, but you still have to do the averaging.
Yeah, and that's why it's 2 different ways of solving this equation. There's 2 different ways of solving this equation. You can solve it by making these erratic times the square root, or you can solve it by giving them some organized pattern that reproduces the average. And the first one is what we guess happens in chaotic theories, and the second one is what we guess happens in integral theories.
But from that point of view, a large M minimal model has an arbitrarily large recurrence period in that sense, right? Because
yeah, the problem with large N minimal models, sorry, by large, what do you mean by large N?
approaching C equals 1.
Approaching C equals 1. I think that they're still integral, right? The number of states is larger, but there's a huge number of symmetries. So I don't think that.
I mean, in some sense, the dimensions are irrational with an arbitrarily large denominator, so it takes a long time until you realize it's integral.
Okay. That's also true of, like, you could say the same thing about the irrational boson. It's true that they're irrational numbers, but the spectrum is still very regular. You can write it down. You know, it's not impossible. I do think that there are similar statements that are probably true even like in rational CFTs. You know, for example, holomorphic modular forms are very discrete objects which satisfy Bootstrap-like equations, and there are properties of those holomorphic modular forms that are random. This is an interesting topic in math, and the same thing is probably true like of rational CFTs. But I don't think it'll quite be a statement. I don't think it can be this statement exactly.
Sorry, Tom, just to be sure I got it. So today you have been shown a way to compute using the formula Kirchner and Hartman, that this formula applies. So we derived this formula with an average. Now, if I understand correctly, we are essentially in words saying that I can remove the average, the bar, only for sufficiently chaotic theories. But
yes,
strictly speaking, this is what we've been showing.
Yes, we showed this and guessed that.
Okay, just to be sure, because then
it's more than a guess. I mean,
to what extent you can remove this bar, it's actually not totally clear. Right?
Sorry, what?
It's not totally clear because you said the theory shouldn't be rational, it should also, even irrational is not enough, it should be sufficiently rational. So at this stage, it's not totally clear when we can remove the bar, right?
I agree. So it's motivated by ETH, which is definitely true in quantum mechanics in many, many cases. And we're going to show that it has a natural holographic interpretation. That's the only evidence for it. It's really just the ansatz. Yeah.
So what's a diagonal element of this CIJK?
The diagonal element, well, I'm not going to try to write a formula for it because there are various pairings that you can make in those coefficients, but it's similar to an ETH, where you get 1-point functions when two of them are the same.
Question about crossing symmetry. So is your ETH compatible with crossing symmetry, or do we have to check it?
Well, it depends what you mean. If you mean that these are some numbers, some fixed numbers, then I wouldn't know how to check that. So maybe there's some way of checking that, but I don't know how. If you mean we're going to average over these numbers, then it is consistent with crossing symmetry on average, which I might check tomorrow, but that's the statement.
Sorry, just a related question. So these formulas are up to prefactors, right? Like you said.
No, well,
up to order 1 prefactors, even the one in the box, right?
No, if you use the exact formula for C0, then this here is just the statement that it's true asymptotically, and that there's some corrections depending on the averaging, but all the prefactors are known. The relation to Liouville had a prefactor that I didn't write, but it's known. Yeah.
Well, I'm just imagining if we also have like a statement of what is the spacing of so here we have the ansatz of like what's the average like OPE coefficient square, right? So if we also know the spacing of the states in the heavy limit, and then like we can just make an ansatz and plug in some numbers of this. So in the crossing equation, so we just say like the sum over blocks beyond some threshold is just given by those numbers, and we just numerically sum them over, and then check the consistency. Is that?
Well, yeah, but do you want crossing to be exactly satisfied? There are dots and subleading terms here, and so you would have to say what you mean for it to be satisfied.
Boundary and non-Gaussianity or something.
Yeah, I don't know. It would be. I think that's a question that we should study. Is to what extent is randomness compatible with the bootstrap? I think this is an important problem, but I don't think we know much about it other than to say that if you do the average here, then lots of crossing equations are satisfied. The usual logic with ETH is that you impose all the consistency conditions that you know, and then it's as random as possible subject to those consistency conditions. And in conformal field theory, it would be very natural to impose crossing first and randomness second, right? It really should be random subject to the bootstrap. That would be a more accurate version of ETH, but we don't know how to do that. I think it would be very interesting to try to build an ansatz where exact crossing is built in. Yeah.
When you say crossing is satisfied, is it just because you have those deltas and the permutations, you just end up writing the identity in all the different channels and it's trivially consistent?
That's how it works, basically. Yeah. Not every crossing equation is satisfied, but lots of them are satisfied for the reason that you just said.
How far, like, if I do that, add these permutations, and then consider something like 2D Ising or something, where I know the exact answer for some complicated object, like, I don't know, 4-point function squared or something, and I just compute it using your method of just looking at the vacuum contribution and some over different channels. Am I going to get something, like, if I compare it to the Ising answer, is it going to be, even though it's not chaotic, do I get something?
It's like true on average?
Yeah, like spectral form factor kind of works for
I don't know, it's a good question. It's a good question. You know, I'm gonna do some calculations tomorrow of like averaged correlator squared, for example. And my focus will be on the holographic case, but I absolutely think there's some calculation to be done there in the non-holographic case, and we just don't know how to interpret it.
Okay, let's thank Dominic.